After watching this video lecture series, students will be able to diagram formation of ionic bonds and understand the driving forces behind the bond formation. You're also going to be able to understand lattice energy and relate the relative values to ionic compounds and their features, such as melting point and things of that sort. So an ionic bond consists of basically two differently charged atoms that are attracted through electrostatic interactions. So basically what that means is we have one thing that's positively charged and one thing that's negatively charged, and they attract each other to form an ionic bond. Now this usually occurs between a metal and a nonmetal, such as, let's say, sodium ion, okay, and a chloride ion to give us NaCl. Okay, however, we could also see an ionic bond form between a ion that is positively charged that is not a metal, okay, and non-metal anion to give us this type of ionic compound. So basically the concept is that you have a positively charged ion interacting with a negatively charged ion. Most of the time that'll be between a metal and a non-metal. However, there are exceptions, as we see here. So when we actually form an ionic compound, we need to think about what actually physically happens. Okay, so what physically happens is that we first start out with two individual neutral atoms. Okay, and the neutral atoms are basically going to either transfer or accept electrons depending on their specific needs. So if we go ahead and look at sodium atom here, sodium has one electron in its outermost shell. Okay, so in order to be like its nearest noble gas, sodium is willing to give up an electron. On the opposite side of that, chlorine has 7 valence electrons and is in need of an extra electron in order to be like its nearest noble gas. So in order for both of them to obtain the octet that will confer stability, the sodium is going to transfer an electron to the chlorine, and subsequently you're going to form a sodium cation and a chloride anion. Now, the positive and negative charges of these ions causes that electrostatic interaction, and the attraction between these two ions is what creates that ionic bond. So, as just a rehash of what we just talked about, basically what's going to happen is your atoms are going to lose or gain electrons, and basically they're going to do that depending on what they need. The attractive forces, or those electrostatic forces that occur, are going to happen because of the opposite charges of the ions that are produced. And the strength of these interactions, which is a new concept, is going to be dictated by the size of the charge. Okay, so the larger the charge on the ions, the stronger the electrostatic interactions. And the stronger the electrostatic interactions, the stronger the ionic bond. Another way to look at this type of bond formation is to look at it with respect to ionization energies and electron affinities. So atoms that have low ionization energies, which are typically metals, are going to be those that want to give away electrons. And atoms with high electron affinity, the ones are going to be the ones that accept those electrons from those metals. So basically, we're going to be forming ionic bonds when you have an element that wants to give up an electron in order to be like its nearest noble gas, and one that wants to accept it. Now, in order for it to give away electrons, it needs to have a low ionization energy. That needs to be an easy process. And elements that need to accept electrons, or want electrons in order to have their octet, need to have a high electron affinities in order to facilitate that type of transfer. Ionic compounds are typically crystalline and very, very structured. If you look at the diagram here, the sodium chloride lattice structure, you'll notice that you have a repeating set of ions. You have chloride, sodium, okay, and this continues all the way down through and across the solid. Okay, so this repeating structure, or this repeating lattice, is what we come to expect or anticipate with ionic solids. In that same thought process, they also are very brittle and have high melting points. The reason why they're very brittle is because any disturbance in the interactions between the ions in the lattice lead to repulsive forces. So if I were to take a hammer and hit the row of atoms right here, and basically shifted each one of these atoms down by one, what you would end up with is negatively charged ions being in close proximity and subsequently repelling one another. So whenever the structures of these ionic solids are disturbed, you end up with a crumbling or basically a disintegration type result because of those interactions. Now, the high melting point is due to the high lattice energy because of the overlapping and sequential organization of the interactions between the sodium and chloride ions, or the positively and negatively charged ions. And we'll talk more about this feature here in a second. So now that we've gone ahead and looked at the structural components of ionic compounds and discussed some of their relative features, we're going to go ahead and talk about the driving force or the determining factor for things such as their high melting point. Okay, and the lattice energy is going to be the main driving force there. So lattice energy is the change in energy that takes place when separated out gaseous ions get packed together to form a solid. So in the context of an ionic compound, we take our ions that are in their gaseous state, we condense them down, and we form that lattice structure that we've been discussing on the previous slides. Okay, so in this process, we're going from a higher energy state to a lower energy state, okay, and heat or energy gets released during that process. Now, because of the definition that we're using, we are going to end up with negative lattice energies. Now, some texts define the enthalpy of the lattice energy as basically going from a solid to the gaseous ion. So basically the reverse of this process, going from the lower energy system to the higher energy system. So in those contexts, you're going to end up with positive lattice energies. But we will be using the definition above, so the lattice energies in our text should be negative. Now, the reality of it is that lattice energy is really difficult to measure directly. The reason why is because you have to put a lot of energy in to an ionic solid in order to basically get those ions in the gaseous state. So most data that is obtained about lattice energy is actually calculated utilizing Hess's law. As we know, Hess's law allows us to utilize equations or processes that we are able to measure and sum those processes to give us the energetics associated with a process that is not able to easily be measured. So if we look at these individual processes, you can see that we have steps initially that take our solid into the gaseous phase, at least part of it. Okay, the next step, you can see sublimation of that solid. In the next step, we are placing or ionizing that lithium gas. Okay, and then in another step, we are also going to be breaking apart the molecule of fluorine. Okay, and then our electron affinity value here can be measured as well, and we end up here with our our lithium and fluoride ions in their gaseous state phases. Okay, now the sum of each of these processes is going to give us the energetics values associated with these ions in the gaseous phase. Okay, and when we transition from this higher energy system to the lower energy system, with the lithium fluoride solid, we're going to release that quantity of energy. Okay, so basically this indirect approach to the lattice energy is what we are able to calculate, taking into account and taking advantage of Hess's law's capabilities. So now that we looked at how lattice energy is measured, let's go ahead and let's discuss how we can utilize charges and distance between ion centers to determine relative lattice energies. So this equation here represents the relationship of lattice energy to both charge of the ions and the distance between the ions. So as you can see, there's a direct relationship between the charges and lattice energy, and there's an inverse relationship between the lattice energy and the distance. Okay, Okay, so the reality of it is, guys, I'm never going to make you calculate lattice energy using this equation, but you need to understand the direct and inverse relationship between the variables. Another thing you guys need to understand is that charge size is going to be the bigger determining factor for lattice energy than the size or the distance between the nuclei or the ion centers. So do not stress about doing these calculations. Just basically understand that there's a relative relationship between the energies and the charges and the distances between those charges. Okay, so if we go ahead and we look at the lattice energy here of magnesium oxide versus the lattice energy of sodium fluoride, you recognize that basically the lattice energy of magnesium oxide is about 4 times that of sodium fluoride. Okay, and if we look at this with respect to the lattice energy and its relationship to the charges, okay, the reality of it is that the +2 charge and the -2 charge relative to magnesium oxide versus the +1 charge and the -1 charge related to the sodium fluoride, basically those values that we have here are going to give us 4, okay, and the values here are going to give us 1. So basically we would expect, if charges were the only determining factor, for magnesium oxide's lattice energy to be approximately 4 times the lattice energy associated with sodium fluoride. Now, obviously, this is approximation. We didn't really consider distance in this problem, but the reality of it is that approximately these relationships to lattice energy and charges are going to be the main determining factor for making relative assumptions. Okay, so let's go ahead and let's apply this thought process with this example below. So they've told us to arrange the ionic compounds that we see here in order of increasing lattice energy. So remember, because there's a direct relationship between the charges and lattice energy, the larger your charges, the larger your lattice energy. So we always first want to go ahead and take a look at our relative charges. Okay, so +1 -1, +1 -1, +2 -2. Okay, so in this context, if we're looking at charges alone, we know that calcium oxide is going to have the largest lattice energy. Why? Because lattice energy is directly proportional to charges, and calcium oxide has the largest charges. Okay, so now we have to decide between sodium fluoride and cesium iodide. Why? Because they have the exact same charge distribution. Okay, so now in this context, that's when we have to look at the relationship between our distance and our charges. Okay, so in this context, when we're looking at sodium fluoride and cesium iodide, the charge values are going to be the same. So distance in this context is going to be the determining factor. Okay, now if we increase the distance, we're going to decrease our lattice energy. Okay, so if we go ahead and we take a look at this, we're going to notice that sodium and fluorine are higher on the periodic table than cesium and iodide. Okay, so the reality of it is that cesium and iodide are going to be bigger ions. So since they're bigger ions, the distance between their centers is going to be larger. A larger distance is going to lead to a lower lattice energy. Okay, so what that's going to mean is that our cesium iodide is going to have a lower lattice energy than our sodium fluoride. Okay, so this is how you're going to go through and utilize this equation. Again, you're never going to do actual mathematical calculations, but you're going to basically do thought experiments that will lead you to the relative comparisons that we see here.